All right, so today we're diving into these really cool handwritten notes to unpack the world of hydrostatics. Sounds complicated, right? But it's really just the physics of fluids that are just sitting there. And you'll see how a couple of super simple ideas can lead to some seriously powerful stuff. Let's jump right in.
So here's the plan. We're going to start with the absolute basics. What even is fluid pressure? Then we'll see what happens when you go deeper. After that, we'll get into a really cool rule called Pascal's law, see it in action with a hydraulic press, and finally wrap up with how we actually measure the stuff. Simple as that. All right, first things first. Section 1. What exactly is fluid pressure? I mean, before we can even get to the cool stuff like hydraulic lifts or, why your ears feel funny at the bottom of a pool, we have to nail down the absolute core concept, the foundation of everything else we're going to talk about today. Okay, so picture this. You've got a fluid, say water, in a container. It's not just sitting there passively, it's actively pushing out on every single surface it's touching. The bottom, the sides, everywhere. And pressure? Well, that's just our way of measuring how focused that push, that force, is on any given spot. This single idea, folks, is the bedrock of hydrostatics. And it all comes down to this super simple but incredibly powerful little formula. P equals F over A. Pressure is just force divided by area. So what does that really mean? It means if you keep the force the same, but squeeze it into a tiny little area, the pressure just goes through the roof. It's the whole reason a needle can pop a balloon so easily, right? You're concentrating all that force onto a single point. Okay, on to section 2, the pressure of depth. Now that we've got the basics of pressure down, let's add one more thing to the mix, the weight of the fluid itself. This is where things get really relatable, because it explains something I bet almost all of you have felt before. Just think about the last time you were in a swimming pool. As you go deeper and deeper, you start to feel that weird pressure in your ears, right? Well, why is that? It's because you've literally got a column of water stacked right on top of you, and all that water has weight. The more water above you, the heavier that column is, and boom, more pressure. And check this out, there's a really neat little formula for this. Pressure equals rho, that's the Greek letter for density, times g for gravity, times h for height, or depth. So what's the big takeaway? The density of the liquid and gravity are pretty much constant, so it's really all about h. The deeper you dive, the bigger h gets, and the pressure just keeps climbing. It's that direct. All right, section 3. This is where things get really cool. We know pressure is a thing, and we know it gets stronger the deeper you go. But now we get to Pascal's law. This is the principle that takes everything we've learned and turns it into a tool for doing some truly amazing things. Seriously, this is a game changer. So here's the magic trick. Pascal's law basically says this. If you take a fluid that's just sitting there and you push on it in one spot, that pressure doesn't just stay there. It doesn't just go in one direction. It gets sent out perfectly and equally to every single nook and cranny of that fluid. Nothing is lost. It's like a perfect message delivery system. And if you're wondering, how do we know this is true? Well, the proof is actually really neat. If you look at this little drawing from the notes, imagine a tiny little triangle of fluid just floating there. For it to not move, for it to be perfectly still, all the forces pushing on it from the surrounding fluid have to cancel each other out perfectly. And the only way that can happen is if the pressure from every direction is exactly the same. Okay, section 4. The mighty hydraulic press. So we've got this awesome law, right? Pressure gets transmitted everywhere. The big question is, so what? How do we actually use that? Well, let's look at the classic example, the one that really shows off its power. This thing, the hydraulic press, is basically Pascal's law in real life. Here's how it works. You push with a little bit of force on this skinny little piston. They call it the plunger. That creates pressure in the fluid. And thanks to Pascal, that pressure shoots through the whole system and pushes up on a much wider piston over here, the ram. Small push in, giant force out. So let's put some numbers on this using the example from our notes. We're pushing on the small side with 400 newtons. Now, to put that in perspective, that's like pushing with about 90 pounds of force. And we're doing it on a tiny plunger, only 30 millimeters wide. But the other side, the ram, is way bigger, 200 millimeters across. Let's see what that size difference actually accomplishes. And the math here is actually super simple. It's just 3 steps. Step 1, we use our little push to figure out how much pressure we've created. Step 2, Pascal's law tells us that exact same pressure is now over at the big piston. And step 3, we just see how much total upward force that pressure can create on that bigger area. Easy, right? And the result? You're not going to believe this. Our little 90-pound push creates almost 18,000 newtons of force on the other side. That is a force multiplier of nearly 45. Let that sink in. We are lifting something 45 times heavier than the effort we're putting in. And it's all because of this simple idea of sending pressure through a fluid. That is just incredible. Okay, last section, section 5. This is about actually measuring pressure. Before we finish up, we really need to get clear on how we talk about pressure because it turns out there are 2 different ways to look at it, and the difference is super important. So let me ask you a question. When you check your tire pressure and the gauge says, say, 32 psi, is that the total pressure inside your tire? It kind of feels like a trick question, and, well, it is. The answer is no, because that little gauge you're using is designed to completely ignore the pressure from the atmosphere that's already pushing on everything, everywhere, all the time. This leaves us with 2 different kinds of pressure. The number on your tire gauge, that's called gauge pressure. It's always measured relative to whatever the atmospheric pressure is right now. But the real total pressure inside that tire, that's absolute pressure. And that's measured from a true zero, from a perfect vacuum. And this diagram from the notes just lays it out perfectly. See that bottom line? That's absolute zero pressure, a vacuum. Atmospheric pressure is this constant baseline we live in. And the gauge pressure, what your tire gauge reads, is just the extra bit on top of that. The absolute pressure is the whole thing, from the very bottom all the way to the top. So it all comes down to this one simple equation. The real pressure, the absolute pressure, is just whatever the atmospheric pressure is, plus whatever your gauge is telling you. So yeah, next time you fill up your tires, just remember, the number you see is only part of the story. There's this whole other layer of invisible pressure you're not even accounting for. So there we have it. We started with a simple formula, force over area. We saw how the weight of water adds up the deeper you go. Then came Pascal's magic trick for sending pressure everywhere. We saw that in action lifting crazy amounts of weight. And finally, we sorted out the difference between what your gauge says and what the real pressure is. That's a pretty solid tour of hydrostatics, right? And that brings us to one last thought to leave you with. We saw how this simple idea can lift a car, but where else is it hiding? Think about the brakes in your car, the landing gear on an airplane, even your own heart pumping blood. This principle is literally everywhere, working quietly in the background. Now that you know what to look for, I bet you're going to